Hello everyone, my name is Chayanjit Ghosh and I am doing PhD in the EC department at the University of Utah. Today I want to talk to you about a novel low power technique for eye tracking and distance ranging. Using two pairs of scleral coil, our proposed eye tracking system is low profile and therefore suitable for integration with smart contact lenses. In adaptive optical system, it is imperative to know that the distance and location of the object of interest for proper image focusing, which can be obtained by accurate tracking of the eyeball. Conventional eye tracking techniques based on scleral coil are bulky, which renders this technique ineffective for applications such as smart contact lenses, which require low power and low profile distance ranging techniques. In our proposed system, we use four coils, two half circular coils placed on the scleral region of each eye. And depending on the system configuration, we drive either one or both the coils of one eye using an AC voltage source and measure the induced EMF on either of the two coils placed on the other eye. This eliminates the requirement of any bulky external coils and reduces the power requirement for the entire system. The induced EMF on the receiving coil depends on the gauge angle dependent mutual inductance between the source and the receiver coil, and therefore measurement of the EMF provides accurate estimation of the gaze angles and object distance. The procedure for eye tracking using our proposed technique involves applying an AC voltage and source on the source coil and simultaneously measuring the induced EMF on the receiving coil for different gauge angles. From the measured EMF, the gauge angles are obtained using a predetermined radial basis function, which correlates the induced EMF of the gauge angle. Finally, the obtained gauge angles are used to determine the object distance using triangulation techniques. A discrete point data set consisting of induced EMF as a function of the discrete gauge angles and object distance was used to construct the radial basis function. The angle-dependent mutual inductance and by extension the angle-dependent induced EMF is shown under the section of electrical modeling. As shown, the mutual inductance depends on the radial vector r, which is a trigonometric function of the gauge angles alpha and beta. The induced EMF is proportional to the mutual inductance. The fabricated coils were mounted on spherical balls placed at 60 mm apart and driven by precision stepper motor. The eye tracking system was operated at resonance under two configurations. For configuration A, the inner source coil placed on one eye was driven with a voltage of 20 volt peak to peak, and the induced EMF was measured at the inner coil of the other eye. For configuration B, both coils on one eye was driven with a voltage of 20 volt peak to peak, and the induced EMF was measured on the outer coil of the other eye. The measured EMF under configuration A as plotted against the bearing angle and the distance of the object and the eyeball is an even signal. On the contrary, the configuration B was observed to be an odd signal. One must note that the object distance is presented here in diopter measurement, which is the inverse of the object distance. Using the radial basis function, we were able to predict the object distance and bearing angle from the measured EMF with an error of 0.1 diopter and 0.4 degree respectively. The energy consumption for the system for a single reading is about 22 microjoule. Thank you for your attention.